All right, let's take a look at some more questions that deal with equilibrium. So just a quick recap here from that first instructional video. If the two charges have the same sign, what we know then is that the equilibrium location is in between the two charges, but closer to the smaller one, because that smaller one needs it to be closer to have the same size force. If they're opposite signs, so one's positive, one's negative kind of thing, it's going to be outside of the two charges and on the side of the smaller charge. So what we usually do is a Kahoot here, but in this case, we're going to do it as a Socrative just so you can do it on your own. So go to Foster 217T and go through those questions. I think there's 6 of them that go with this, and then there's another 3 at the end that go with just how is that force equation set up. Okay, go ahead, hop over there, do those, and then come back and finish the video and we'll go through that example. All right, so you checked on Socrative. You did well. Good. So now our first question is, we're going to look at this example right underneath where it says Kahoot on page 3. And we have two charges. We have a positive 2 nanocoulomb at x equals 0 and a positive 4 nanocoulomb at x equals 1.5 meters. And I want to know, where is the equilibrium point? So we notice they have the same sign. Okay, so same sign means that it's going to be in between the two charges and closer to the smaller one. So we are going to put it in between the two charges. So in between, but closer to the smaller one. So halfway is the 0.75 meters, so I'm going to put it just here. This is where I'm going to put that unknown charge, and we just give that unknown test charge Q. There doesn't actually need to be a charge there for it to be an equilibrium point, but we'll just call the value there capital Q so we know which one is going to be common and which one's going to cross out for us. So now that we have this set up, and again, the reason it's in between is this positive charge is pushing it this way, this positive charge is pushing it that way, because our test charge is always positive, and we see that we have opposite forces. Great. So what that means for us is that now I can say that those two forces are going to be opposite and equal to each other. So when I sum up the forces, set it equal to 0, I'll move one over to the other side, and so those two forces have to be equal. All right, so let's substitute in. So I have K times the forces involved from 1. So I have the Q1 times Q divided by how far away it is. All right, so we don't know where this equilibrium location is. So here's when we go back to our green sheet and we follow those steps. So the first step is you need to decide that from the origin to our equilibrium location is now called R. If it's on this side, that's fine. If it's way over here, that's fine. If it's over here, that's fine. The distance from the origin to our equilibrium point is defined as R. Okay? So whichever charge is at the origin is always going to be divided by R squared. Now the other one, so again, now we're going to have K times the two charges involved. In this case, it's going to be charge 2 and the equilibrium test charge, Q, because those are the two charges involved in that force, divided by its distance. And so this is the distance you have to figure out. So looking at my picture, I'm trying to figure out what is that distance there. So I know this whole thing is 1.5. So if I take off an R, I'm left with this. So this is going to be 1.5 minus R. Now, as you do these problems over and over again, it's going to feel like it's the same answer every time. And sometimes it'll be like 1.5 minus R, sometimes it'll be 1.5 plus R, sometimes it'll be R minus 1.5. So it's going to look similar. But again, figure that out before you put it in. So putting that down on the bottom, I have 1.5 minus R squared. All right, at this point, a bunch of stuff cancels out for us. Then we get to put it into either a polynomial. I'm going to show you solver, and then we get our answer. So what's going to cross out for us? The K values are going to cross out. That's for 1. And I also have a capital Q on both sides. Those cross out. Remember, these absolute value signs are there for a reason. So when you do type these charges in, make sure you're just typing in the positive values. All right. So what we're going to do now to kind of set ourselves up is we are going to do a little cross multiply. So now I have Q1 times 1.5 minus R squared equals Q2 times R squared. I personally like to always divide this Q1 over here. The reason I like to do that is because typically these will have the same exponents, so it'll be like nano and nano, and so you can get that times 10 to the negative 9 divided by 10 to the negative 9. They'll cancel out for you when you do that. So I will divide the Q1 over, and then I will subtract that whole squared term over. So now I have 0 is equal to Q2 divided by Q1 times R squared minus the quantity of 1.5 minus R squared. And so now I just need to put that on my calculator. So let's go ahead and flip over and substitute that in and put it on our calculator. So our 10 to the negative 9s cancel for us here. That's why I like to divide those two charges. If you have one charge with each one, they still cancel out as well. So you can do that as well. Now I just need to type this into my calculator. So I have 4 divided by 2. So I'm going to use solver on this one since I got it set equal to 0. So go up, clear out your other one. So now I have 2x squared minus the quantity of 1.5 minus x quantity squared. And we always want the positive solutions. There's two solutions. There's one solution that's negative, one solution that's positive. So I'm going to go ahead and pick my positive solution. I'm going to pick, say, 0.75. And oops, I got to hit enter there. Hit enter. Choose my positive solution of 0.75. I'm going to guess at, hit alpha solve, and I get an answer of 0.62 meters as my solution. And that works.